Thank you for bearing with us, everybody. Thank you, Megan, for joining. And thanks in advance, Gary and Beth Ann, for being our student panelists. I'm going to mute me here. Stay on. Okay. You have me here. You have me here. So thank you, Megan, for joining us. Without any further additional delay due to technology incompetence on my part here, I'm going to ask Megan to please go ahead and start your talk. You have slides to share. Yes, great, excellent.
Could you?
Yeah, there we go. Thank you, Megan.
Okay. Can you see my slides?
I can see you.
Right. Hold on. I shall share my screen, hopefully. And share. Okay. Can you see the slides now?
Yes. Yep.
Okay. Right. Well, thank you for inviting me to give this talk, which is a subject I've worked on long and hard, as Gary knows, and very, very active, very actively. I'm Professor of Food Physics at the University of Leeds. I'm also the Food Supply Chain Theme Leader on Leeds University Smart Farm. So things got a little bit delayed by COVID, but here we are. So today I'm going to talk about food reassurance, sustainability, robotics, and sensors. And what I hope is a vision for the future of food. We certainly do need a vision for the future of food, given the threats, war, energy, climate change, supply chain threats, and poverty. All these are essentially existential threats. In fact, they're so serious that we may be looking at the demise of some of the small and medium enterprise manufacturers, which in the UK, which would be a disaster. So there's really needs to be action here. And here we have the expertise to be able to transform food systems into a sustainable future. So let's just have a look at, first of all, food supply chains today. Can I just do a sound check? Can everybody hear me and see the slides properly?
Yes, for sure.
Okay, right. So continuing, food supply chains today are opaque, they're complex, they're fragmented, they're non-verifiable, they embody many commercial risks, they embody many health and safety risks, and of course foodborne disease is not the least of those risks, and we have had a number of examples of that. And of course COVID itself may well have been spread through the food chain initially. Sustainability is hard to test, and actually the evidence is there's very little that the current food system is unsustainable. And then we have disputes between buyers and sellers that we don't hear very much about, but cause considerable disruption. So there's a challenge here for us. And in terms of reassurance to everybody involved in the food supply chain, we really need insights into individual items. And currently, labels and certificates pertain to the entire production line, not to individual packages. And when you start looking at the variation in manufacturing, many individual packages can be below standard. So we really do need a 100% inspection. And I would argue that 100% inspection is within technology's reach. We don't have it, but it's possible. At the moment, we have reliance on the honesty and competence of a central party, and governments and companies are the only enforcers of standards and often fall short of what is desired. Finally, we have misleading or incomplete labels. So, for example, in the United Kingdom, processing aids need not be on the label. So, for example, in chocolate, there is a relatively considerable amount of polymethyl siloxane, which is a lubricant in the conching process. So there are other challenges as well, because of the way the market competition and species standards are set, small and quality producers may get squeezed out. There's fragmentation and opacity of supply chains, and in particular, global supply chains are difficult to manage. Unsustainable resource use, which we all know about, and of course, the food and agriculture production system is one of the biggest contributors to global warming gases. Sorry, I've just lost my complete use of English. Not a great thing to do when you're giving a talk, but never mind. So the result is a low level of trust in the food system. Now, consumers and governments are interested in the safety, authenticity, and quality of food commodities. And we really need sustainable food production. And in the current climate, especially agile manufacturing, capable of meeting supply chain challenges. So, for example, raw material changes can be very challenging. Even, for example, if you change in a chocolate manufacturing process from West African cocoa butter to South American cocoa butter, the manufacturing processes may have been optimized for West African, and then the Brazilian causes lots and lots of problems and raw material losses. The main food quality traits that we would want to be able to measure using non-invasive sensing techniques are sensory techniques, chemical composition, physicochemical properties such as structure, health protecting properties, nutritional characteristics, and safety. So this is a challenge, but I will argue that this is not an insuperable challenge, because there are a wide range of non-invasive sensing techniques, from optical, acoustical, electrical to nuclear magnetic, X-ray, biosensors, microwave and terahertz sensing systems. Some are in experimental in the laboratory, others are being applied as we speak. However, there is also a need for an appropriate regulatory framework which acts to exclude unwanted components in foods and includes the needed components, with economic sensors incorporated into food packaging as part of a reassurance framework supporting sustainable production, a circular economy, regulation and food chain management. And this requires a revolution in manufacturing, in food manufacturing. But it's a revolution, I'd argue, that either we carry it out or we're in serious trouble, to put it mildly. The integration of these sensor modalities into a single technological and commercial platform, and I would emphasize the platform requires standards and it needs to be commercial and it needs to use off-the-shelf components. And we're a long way from this at the moment. But we could use blockchain technology, for example, to integrate the data to carry out the supply chain tracing that we need. And this kind of smorgasbord of sensing and technology, digital technologies and so on, offers us the opportunity for a paradigm shift in food reassurance and manufacture. Just a comment to Elizabeth, the chair, please give me a 10-minute warning. I tend to talk as a stream of consciousness, so I might kind of need a reminder of time. Okay, so just looking at the totality of sensing techniques, there is a very wide choice of technologies and modalities available to us. And these were summarized by myself and colleagues in 2016 in an article in The Analyst, the references below. So I'm not going to dwell on this. If people have questions about any of these modalities, I'm happy to answer those questions. Okay, so one of the issues in terms of the sensors is the way they're deployed and also the length scales on which measurements are being made. So if we start from the longest scales, this would be agriculture and using satellite sensing to look at the optical, usually optical or infrared or ultraviolet emissions from agriculture and using that to characterize crops. Nowadays, we have drones. So, for example, on the Leeds University Smart Farm, we have a headwall hyperspectral camera suspended on a drone. And then we also have the same camera, not the same camera, the same make of camera in the laboratory, so that we can compare the spectral lines that we're seeing from the crops with particular, say, nutritional factors that we're interested in, and identify, for example, single line, very low, very economic sensing techniques using drones. We're using a robot as well to towing instruments around in the farm. And we can use microwave mapping on all scales of mobile water through the dielectric factor. This can also be done in greenhouses and in factories. And then when we're close to the line, we can use non-invasive techniques, acoustic, electromagnetic, optical techniques to look at what's happening on the production line. So in terms of a concept, we do have a very wide choice of sensors and modalities. And within this, the real challenge is assembling all the data into a single place. And this raises one of the big research challenges where you have data from all sources, which is if you've got a big data set, what can you learn from that data set that is not apparent in any of the single data streams that's coming into that data set? And then I'm going to illustrate how we might begin to use Bayesian techniques and artificial intelligence, physics, constrained intelligence, and these different machine learning techniques. I want to just start with one modality. This is hyperspectral imaging. So just to exemplify this, first of all, let's say we're looking at a fish on the left. Then the images captured by the hyperspectral camera, each pixel will contain the entire wavelength information. So for example, on the camera we have, we get data between wavelengths of 400 nanometers, that's in the near UV, and then up to 1200 nanometers, so we're getting up into the near infrared. And these images can all be stacked in different ways in order to produce a signature. What we're interested in is, in fact, is because of the expense of these cameras. I mean, you're talking around over £100,000, and if you're running it on a drone, you're talking. You also need trained operators and so on. So it's expensive. We need, if we're going to transform the food industry, we really need very low cost sensors. So the idea here is that we could identify a single or maybe two spectral lines that are signatures of particular components in the food. And I will illustrate this later in my talk. Okay, so here's some more. This is the nano hyperspec camera that we have. And I'm not going to dwell on this here, but this is an illustration of mapping the moisture in an island called Barrier Island using a drone. In this talk, I don't want to dwell on the data you can get from hyperspectral imaging particularly, because for me, it's low-cost sensing systems that are which are required. So as I said, we'll identify key spectral lines and then implement a low-cost sensor system based on a single spectral line or color gradient imaging. So I forgot to click those bullet points into the slide. Okay, so to exemplify the work we've done with my colleagues in Jiangsu University, with whom we've been collaborating for 10 years. Here we have an example of a colorimetric sensor based on the food component curcumin, which undergoes a transition as a function of pH into ferulic acid. And at the top, we can see the color changes that are occurring as the pH changes. So this for example, we might package the curcumin in casein, milk powder, spray dry it, and then incorporate it into a plastic packaging film. And this is an area we've been working on. It's not as simple as it sounds, because the packaging film has to accept the components for example, if you're looking for putrefaction, you might be looking for hydrogen sulfide. It's necessary for that to diffuse into the packaging material, and it can be difficult to develop packaging material so that it acts as a moisture barrier on the one hand, but it allows these other gases into the packaging. So this is not quite as straightforward as it looks. This is some work done by my colleagues on electrochemical writing, where the writing will appear when there is some change in pH, or there's a gas such as hydrogen sulfide appearing in the package. So this is very much work in progress. There are 4 or 5 papers a day being published in this area. It's very, very active. But the actual commercial embodiments in packaging are few and far between. And one reason for this is the economics of packaging, which I'm not going to go into, but we've certainly discovered that even rather low cost marking, is, for example, dielectric and RF on packaging, still is too expensive for the companies to adopt. Anyway, to carry on, currently a lot of the food reassurance testing is carried out offline in the lab using often expensive analytical instrumentation. So there is an interest in using these remote sensing techniques, these new sorts of sensors, and what's called the Internet of Things, to integrate the data so that each sensor may not be giving a very accurate picture, but when all the modalities and all the data is collected together, so we're sharing throughout the supply chain the digitized data, and then perhaps integrating it into a blockchain, then we can have new ways of seeing monitoring and measurement of an entire food distribution chain using these techniques. And this company, Ambrosis, who's there's a reference at the bottom there, is a Swiss company that offers commercial solutions of this sort. Okay, just for information, I don't know, you might all know what blockchain is, but anyway, I'm going to tell you again. Blockchain is a digital ledger in which transactions are recorded chronologically, anonymously, and publicly. So all the data in a blockchain is available to all members of that blockchain. And it's this openness which is the source of its reliability. So any change that is made in the network is propagated from node to node like a spreadsheet, duplicated thousands of times across a network of computers. And this ledger contains a chronological, continuous, and complete record, which is the chain, of all transactions performed. And these are grouped into blocks. And a block is only added to the chain if the nodes, which are members in the blockchain network with high levels of computing power, reach consensus on the next valid block to be added to the chain. And a transaction can only be verified and form part of a candidate block if all the nodes on the network confirm that the transaction is valid And the method of determining this issue is called the consensus protocol. So this is a kind of a diagram of what I've just said. So I'm not going to repeat that, but I believe this talk is being recorded, and you'll be able to look at it afterwards and refer to it. So just to illustrate what I mean by new ways of sensing, we'll just take a simple example. So we have a consumer smartphone which is reading the packaging, and the data is transmitted to the blockchain, and the blockchain registers that the package code is inconsistent. Now we've got the totality of the data throughout that supply chain, and in that supply chain we have sensors in the containers which are transporting the food, and the sensors in the container registered a temperature drop, and the temperature drop is consistent with the container opening. So these sensors are built in such a way as to make them difficult to tamper with, and the inference from all that is that the product was interfered with during transport. Now this is a real example. I can't, well, in pigs are and pork are very important in China. And this kind of thing goes on a lot in the supply chain for pork in the Chinese market. So this is actually, being able to do this was significant as far as the Chinese government were concerned, because politically they want to keep the people who buy pork in China happy. Okay, so how are we going to go about making all this real? Well, we proposed a sustainable food manufacturing research hub, and this involves my colleagues at Jiangsu, the Leeds University Smart Farm, and a multidisciplinary engineering research team from Nottingham, Birmingham, York, Imperial College, Simon Pearson, Lincoln, Greenwich, Edinburgh, Reading, South Bank University, Sheffield, Hallam and Loughborough, which between us combine all the disciplines that are needed to begin to implement this transformation in food manufacturing. So in order to achieve a sustainable food manufacturing system, we do need to be looking at the farms, we need to look at the supply chain, we need to look at the factories and the distribution, and also what happens in people's homes as well. So we need a systems approach where we look at the totality of the process. And in doing so, we'll look at the way in which energy is used throughout the chain. So for example, if we look at the chain as a whole, it may actually be more effective and sustainable to use more energy in one place in order to greatly reduce energy and waste and reduce the processing in other places in the process. Also, given the supply chain threats that we're facing, very often product now needs reformulating as the raw materials coming in change due to climate change, due to the way transport problems. So we know what's happening with Ukraine. Ukraine and Russia supply 40% of the world's grain, and a high proportion from Ukraine of sunflower oil. One question is, what can we do, for example, with the waste oil? And frankly, burning it as biofuel, in my opinion, is absolutely unsustainable way of going forward. So we need to look at the chemistry of vegetable oils. Can we use them for other purposes? For example, in what are called cold thermal storage fluids. So if people want to know about these things, I'm going to leave lots of time for questions. This is the kind of overall picture. I see I've just underused my time, but I'm sure that people will have plenty of questions. So this is the summary. Thank you for your attention. And I've left an awful lot out of that talk. And Gary can fill in the gaps.
Thanks, Megan. I don't know if you can hear me. Can you hear me now?
I can hear you. Yes, I can hear you.
Okay, so we have our two student panelists who are going to ask questions, and looks like Gary's all queued up to go first. So Gary, please start.
Hi there. Thank you. Thanks. Thanks, everyone. So, Megan, thank you very much for the talk. It was lovely to hear you talk about the subject. It's one that's always very close to my heart. That's always on my mind. I've got a couple of questions, and I'll ask them, I suppose, as we go through the conversation. One of your papers I've recently read talked about, obviously, non-invasive sensing, but also talked about the size of and portability of the artifacts. And one of the challenges was really about reducing the size of these and making them fit maybe on end effectors or on the end of robots or something, so you can do something in real time, maybe inline packaging. Do you see anything that, do you see a sort of a 5 or a 7 year plan where we can get something that is not offline, but sort of in field real time? Is that something that you can see in a short amount of time that can be integrated into robots? And then I've got questions around blockchain later.
Oh, okay. Well, yes. I mean, on the smart farm, currently we're building a ultrasound system for soil mechanics testing and moisture, looking for things like poaching in the soil, and that's being combined. So definitely the ultrasound can. I mean, the complete ultrasound system costs £3,000. The probes themselves cost about £80 each. So this is definitely economic. It is being combined with the neutron and gamma ray sensors, which are a little bit more expensive. But we're also, what we're doing with the robot, we're also going to fly the drone with the robot so that we can get the hyperspectral image of the soil that's being tested by the acoustics. And that's going to happen this summer. But there are many other, I mean, and I am very keen on these optical techniques because you can implement them so cheaply. I mean, a laser diode is tuppence. And also, these food-based sensors, I mean, potentially they can just be thrown everywhere. They're just powders, and you only one grain, and that's all you need. And because the color changes are so dramatic, and the spectral lines are very sharp, if you find the right chemical sensor, Yes, I mean, to me, the biggest obstacle is commercializing it. Frankly, I mean, we're demonstrating these already in the lab. We're pretty confident they're going to work in the field on the farm, but making them commercial, that is, you know, you may have heard, you know, in terms of technology readiness levels, this thing called the Valley of Death. I mean, my take home is any commercialization is going to cost you 3 million. And it doesn't really matter whether the sensors cost tuppence to make or £1,000 to make. That isn't the point, you know. And also volume. You need to be able to manufacture in volume. You need the marketing and technical support. And this is, and then we're in a recession. Companies aren't willing to invest unless it's an absolute racing certainty. But hey, we're optimists, aren't we?
Thank you, Gary.
Absolutely are. That's the so. Thank you very much for the question. I've got several others, but I'll let the rest of the panel obviously take their turn.
Thank you, Gary. I'm going to go now to Beth Ann for the next question.
Thank you for the fascinating talk. I have a couple of questions. The first one, I was quite interested in terms of food packaging. So the ability to integrate sensors, and obviously it means that you can track it throughout the whole supply chain. And it got me thinking about the end consumer, and obviously kind of use by dates at the moment are what a lot of consumers will base their decision to potentially throw away food that is actually perfectly edible. So do you think that by having so-called smart packaging, it could enable use by dates to become a thing of the past?
Yes, well, yes, definitely. I mean, there are technical challenges, but the other huge challenge, frankly, is packaging itself. You know, so for example, a lot of the metallized film packaging is cannot be recycled at the moment. We are working on techniques for actually printing aerials. I mean, we can print aerials onto packaging so they can be scanned with microwaves. And one of the biggest issues in terms of the waste from packaging is that only around 2% of all the recycled plastic is actually recycled. The rest of it is burnt. And the reason is that it's graded. So the only recycled plastic that can be used as food packaging has to be what's called grade 1. And only 2% of the packaging is grade 1. So what I'm saying is that by developing these in-package sensing methods, not only can we inform the consumer of the product inside the package, but we can tell the waste sorting systems what the plastic is. And one of the biggest issues is in sorting that plastic. But using microwave techniques, which can go through black plastic, that can go through mixed plastic, quite thick layers, then we can begin to address the whole issue of plastic waste, which is a massive issue as well. And
Thank you.
That's great. I'm going to go on to Amy, and then there's a question in the chat we'll come to. And then if anybody in the room here has questions, I'll come to you. So thank you, Beth Ann. Over to Amy.
Thanks, Elizabeth, and thank you, Megan, for the fascinating talk. I was interested to learn a bit more about the sensors themselves. And obviously you can't go into great detail because we don't have the time, but the fact that you focus on non-invasive techniques, and And I was wondering whether we ideally want an instantaneous result from a sensor. How limited are we in what we can detect, and how specialized the sensors need to be? And yeah.
Okay. I think we're just at the beginning, and there are a very few kind of in-package sensors which are expensive. So, and really, for this to have an impact, it has to become very low cost. So that's the first thing. Second, I can't, at the moment, it's hit and miss. It's what is an obvious target. So hydrogen sulfide from putrefaction, it would be one target. pH changes in the product would be another target. But if we wanted to narrow it down, so for example, I think we're a very long way from detecting aflatoxin, you know, or allergens, which would be, you know, important. It would. I mean, if we could do that, then we can actually address a whole range of issues in ill health and so on. But because you're talking about ppm or even ppb, the current sensors that we're using require relatively high concentrations, and of course, whatever it is you're detecting has to come out of the food first. So there are real limitations, and I mean, there are techniques which potentially can actually see inside the food. So MRI, magnetic resonance imaging, and you can start doing chemistry with that. Currently, that technology is, you're talking about a fortune. I mean, it's just, you need these big magnets, and even with the magnet technology. So I'm not saying we will never be able to do it, but there are real limitations. However, we are, you know, we have had some successes, and but it does mean looking at new methods of making the plastic. So we're looking at electrospinning, for example, rather than these web type. Sorry, I've forgotten the words. Anyway, I'll leave it at that. That's a great question, and I can't answer it properly.
No, it was really interesting.
Thanks, Amy. Thanks, Megan. Any questions from the folks in the room here? It's been a long day and it's very warm. So I'm going to go to the question from Romana in the chat. And I don't know if you can see the question.
I
Megan.
can. Hello, Romana. Very pleased to meet you again.
I don't have control to share cameras here. So Romana's questions about the war in Ukraine and border controls. It's questioning the self-sufficiency of food and agriculture of each country. Singapore may be on the top of the list in GDP, but if it is unable to import food, Singaporeans may say we need potato chips, not computer chips. How good is, quote, think globally and act locally in the present context?
Absolutely, yes. I mean, and that applies to the UK. As much as it does in Singapore, even though we're producing over 40% of the food, and which actually in the UK, which actually puts us in a relatively strong position. But however, having said that, the manufacturing processes, I mean, this week I've been around a big factory. If you go around these food manufacturing factories, they have grown like topsy. They are so complex, and they have been optimized for very particular raw materials. And if those raw materials change, the process is scuppered, and the companies do not have the understanding of the product and the manufacturing process to be able to recover. This is why I'm saying that there is a real threat to many of these manufacturing operations purely from change in raw materials, because they've been developed based on a given raw material supply maybe for 40 years ago, and they don't understand the process. So process understanding, and then this product reformulation, and also sensing in process sensing, non-invasive sensing on the product. I really don't think these are optional extras in the UK manufacturing. And yes, absolutely, think globally and act locally, absolutely 100%. And the other thing, of course, is to decentralize manufacturing operations. So there's less processing, more locally produced. And then you can start looking at how you use the waste. So an example is dairy manufacture, where the very big farms are using anaerobic digesters, both to produce energy on the farm and to produce fertilizer. But potentially those ADs could be taking waste from a range of waste, say in a 50-mile radius, and then generating electricity. So the farm vehicles then convert to renewable electricity, that kind of thing. But yeah, sorry, I could go on, but I won't.
Great, thanks, Megan. I'm going to loop back to the student panelists. So Beth Ann, you have another question.
Yes, thank you. I was just wondering if you think there could be a trade-off between leveraging data in the food supply chain as a competitive advantage, as opposed to kind of having everything open to encourage transparency and traceability. And if there is a trade-off, how do you balance it?
Yes, wonderful question. And let's put it like this. There was far more chance of implementing a blockchain in China than there was here. Right, so it was actually, we could actually look at it in terms of pork distribution in China. With the situation that we have of multiple competing companies, and the food industry is more secretive than the military as well. Okay, so there is definitely a problem, and I think we politically, the food industry, maybe it's begun to understand that there needs to be much more collaboration, you know, and actual sharing of data, because the raw materials are shared right the way through the chain. So this kind of very narrow competitive view could actually scupper food production. So yeah, absolutely, there is a trade-off, and I would argue that there has to be far more collaboration. You know, there will always be secrets, at least. Maybe not always, but great question. And yes.
Thank you, Beth Ann and Megan. And over to Gary for one more question.
Yes, thank you. It jumps off Bethan's question, really. So I know when people think of blockchain, they have different connotations in their mind, and it probably gets a bad rap, and the right word to use is probably distributed ledger technologies, and then people tend to sort of think of it a little bit differently. But I feel that there's real value in having an open system, certainly with food supply and food supply chain and reassurance, because it's the one thing that we all need absolutely to sort of live in it. It wouldn't be right to have a closed system where people, and only certain people, can sort of enter that. But it feels maybe that new economic models are probably required, maybe some further incentivization for people to share information, just what you're talking about, really. Do you sort of see that similarly, or have I missed something? What are your thoughts on that, Megan?
Well, I mean, I do think we need new economic models, however, I think we have to start right now, you know, and try to have an impact and deal with what, in my mind, is an existential threat to all of us. You know, so there's an urgency to this, and you know, I mean, we're not going to change the economic model this side of the election. But yes, we do need, but I do think, you know, certainly my interactions, I've had quite a few recently with the food industry, both small, medium manufacturers and the biggest companies, is that they recognize their interdependence and they recognize the need for collaboration. And so I think, you know, like us, we have to be optimistic, and we have tools, we have the knowledge, we can see a way forward that does offer a solution, let's say in a 7-year period, and we should just bloody go for it, hell for leather. And yeah.
Wonderful. Thank you very much.
Thank you. So I've got a quick question, and then we're going to close out. Megan, one of the things that I always wonder about is people talk about blockchain, and I understand, you know, it's great for traceability and things, but blockchain is quite expensive from an energy usage standpoint. And so I always get a little bit nervous when people talk about blockchain in the context of sustainability. I don't know if you have a comment to throw out there.
Yes. Yes, well, I think Bitcoin's totally unsustainable from a energy it's unsustainable. Actually, it's not unbreakable either, you know, and we've seen some, I mean, frankly, it's junk. It's from every point of view. However, if you're looking at a blockchain where people are really collaborating, and there aren't too many transactions. I mean, the problem is every single Bitcoin transaction, I think it's something like 1.5 watts per single transaction. It's extraordinary. So yes, but on the other hand, I mean, if we're looking at a supply chain, there'll be critical points. There's leaving the factory, there's entering the container, you know, and then we only need one piece of data at each of those points. And also we can look at things like, you know, the temperature in the distribution container. So we're not actually monitoring every package all the time. But I think you're absolutely right. I do think that it can be used in a energy efficient and sensible and sane way.
Great, thank you. So let's all thank Megan here at home. Yeah, I would imagine Megan will be happy to hear from people with follow-up comments and questions. Been really enlightening. And I'm going to close out with an announcement for the next seminar. I think April has got a little slide to put up. So in the next seminar is going to be on a different date than usual. We're going to take advantage of a visitor who's coming to LAR, who's called Jackie Baltus, who's a professor in electrical engineering from, he's currently at the National Taiwan Normal University, or NTNU, in Taipei. He is going to come and give, he'll be actually here for 3 days, the 25th through 27th of July, visiting LAR, and he'll give the CDT seminar on the 27th. There will be for those of you in Lincoln, there will be a physical space. There will be another hybrid talk, and we'll let people know where that is once we get the things sorted. This arrangements just got arranged this week. Jackie is an old friend of mine and one of the most creative roboticists I've ever met. So I really encourage people to try to make time to fit in, either meeting with him and or going to his talk. So I will see you all in about 6 weeks time, and it may not be any cooler. So have lots of ice cream and have a good weekend. Thanks, everybody.
Bye.
Thank you very much, Megan, for your time.